Talk about complex numbers. So far in math, you have mostly talked about the real number system, where all numbers were divided into two categories, either rational numbers or irrational numbers. Rational numbers being any number that could be written as a fraction, irrational numbers being numbers that have decimals that do not repeat, there's no pattern to them, and they never end. Examples being anything that has a pi in it or square roots of numbers that don't come out nicely. So far, that has been our concept of numbers. All numbers are real. They're either rational or irrational. Now we're going to add in imaginary numbers into the mix. So we have real numbers and we have imaginary numbers. Both are part of the complex number system. So you can kind of see from this Venn diagram how everything is organized. So where do imaginary numbers come from? Imaginary numbers occur anytime we take the square root of a negative number. So we define imaginary numbers, or I, as the square root of -1. That's down here. So if it's imaginary, if it's not real, why do we have to mess with it at all? And part of the reason for that is even though I is imaginary, because we can't take the square root of -1, there's no real number that when multiplied by itself gives us -1. But if I were to square the square root of -1, I get -1. So even though I is imaginary, I squared is a real number. I squared is -1. And that's going to be really important to some of the operations that we do today with complex numbers. So today is mostly just an introduction into what complex numbers are. So let's practice. If I take the square root of -25, we know the square root of 25 is 5. But how do I take the square root of a -25? So -25 is the same thing as -1 times 25. The square root of 25 is 5. The square root of -1 is I. So the square root of -25 is 5i. Same thing is going to be when we take the square root of -72. 72, this is not a perfect square. So a couple of different ways we can figure out how to simplify the square root of 72. I'm going to make a factor tree this time. So I know 72 is 9 times 8. 9 is 3 times 3. 8 is 4 times 2. 4 is 2 times 2. These two 2's are going to buddy up. These two 3's are going to buddy up. So we're going to have a 3 and a 2 that go on the outside of the radical. This 2 didn't have a buddy, so he stays on the inside of the radical. And because we're taking the square root of a negative, we need an I as part of our answer. So our answer would be 6i root 2. Another way of thinking about that same problem would be I could rewrite the square root of -72 as the square root of -1 times the square root of 9 times the square root of 8, because -1 times 9 times 8 is -72. Square root of -1 is I. Oh, actually, time out. That's not right, because square root of 8 can be simplified further too. Let's do, instead of 9 and 8, let's do 36 and 2. I just had 9 and 8 on my brain because that's how I first divided up 72 with our factor tree. So this is also, if I multiply these out, we get the square root of 72. The square root of -1 is I. The square root of 36 is 6. So we have I times 6. Or 6i, and then the square root of 2. So another way of thinking about it, but this way I pulled out the perfect square instead of making the factor tree. So another example that comes out nicely, -9, the square root of -9 is 3i, because the square root of 9 is 3. So I'm taking -5 times 3i, which is -15i. And here's some examples. You can pause the video and try them on your own. Number 4, square root of negative 12 can be written as negative 1 times 4 times 3. Square root of 4 is 2. Square root of negative 1 is I. And then we have the square root of 3. On the next one, we would do this part first. Order of operations says we do grouping first. The square root of negative 36 is 6i, and then we multiply it by the negative. So our answer would be negative 6i. And then lastly, 54 is 9 times 6. So I can pull out a 3. Here, I'll show you that step. So we've got 2 on the outside. Got 9, 6, and negative 1. So 2 times I times 3 times the square root of 6, which doesn't come out nicely. So 6i root 6 would be our simplified answer here. All right, let's talk about how to add and subtract with complex numbers. For the most part, complex numbers act just like anything, where we're going to combine our like terms. So when we're adding, I'm just adding 8 and 5, the two real components, and then I'm going to add negative I and 4i, the two imaginary components. The only thing that kind of looks weird here is we're going to leave our answer like this. Standard form says the real part is going to be written first, and the imaginary part is going to be written second. So second example, now we're subtracting. So with subtraction, make sure you distribute that negative sign so you don't make silly mistakes here. And then again, we're going to combine our like terms. So when I combine the real parts, 7 and negative 3 make 4. And when I combine the imaginary parts, negative 6i and positive 6i cancel each other out. So our real answer, or our final answer, would just be 4, the real number 4. And then for the last example, we've got a few things going on. First, I'm going to get rid of the parentheses by distributing this negative sign. So 13 minus 2 minus 7i plus 5i. And then again, I'm going to combine my real, combine my imaginary, and then we're done. Multiplying with complex numbers works a lot like multiplying any, in this case, monomial times a binomial. If I distribute this 4i times negative 6 is negative 24i, and 4i times I is 4i squared. The only difference is now we're going to take this a step further. You should never have an I squared or anything higher than an I with an exponent of 1 as part of your final answer, because I squared means negative 1. So really, this is negative 24i plus 4 times negative 1. And 4 times negative 1 is negative 4. So our real component is negative 4. And remember, we write the real component in front. And our imaginary component is negative 24i. So on the next one, we're going to FOIL. I'm going to distribute the 9 first. 9 times negative 4. 9 times 7i. And then I'm going to distribute the negative 2i. Negative 2i times negative 4. And negative 2i times 7i. So negative 14i squared, let's simplify that next. Negative 14i squared is negative 14 times negative 1, which is 14. So really, I have a plus 14 back there. So I'm going to combine the plus 14 with the negative 36 to get our real component. And then for our imaginary component, we're going to add the 63i and the 8i to make 71i. Few more multiplication examples. Negative 3i times 10i. Negative 3 times 10 is negative 30, and I times I is I squared. I squared is negative 1. So we have negative 30 times negative 1, which is 30. On the next one, we're going to distribute the I to get 8I minus I squared. I squared is -1. So that -1 turns into a +1. And we have a positive 8I. Always put the real first, imaginary second. And then another example where we're going to FOIL. Why don't you pause the video and try it on your own to make sure you've got it. And real quickly, we have 3 times 5, 3 times -I, 5 times I, and I times -I. This becomes a +1. So we have +1 plus 15 and -3I plus 5I. The last skill we need to talk about with simplifying complex numbers is if you have an I in the denominator, it's kind of like rationalizing the denominator. We don't want an I in the denominator, an imaginary component in the denominator. So just like when we rationalize fractions, we're going to multiply the numerator and the denominator by the conjugate in order to get rid of the imaginary component. So the conjugate of 1 minus 4I is 1 plus 4I. So we're going to multiply both the numerator and the denominator by 1 plus 4I. Just like with rationalizing fractions, we're allowed to do this because 1 plus 4I over 1 plus 4I is just 1, and multiplying by 1 doesn't change the value at all. So I'm going to start by FOILing the denominator so you can see why we wanted to do this in the first place. So I'm going to take 1 times 1, 1 times 4I, -4I times 1, and -4I times +4I. So the whole reason we did this was because we knew by multiplying by the conjugate that the i's would cancel. And then when I have I squared, remember that's the same thing as -1. So we really have 1 plus 16 in the denominator, or 17 in our denominator. So by multiplying by the conjugate, we completely got rid of our imaginary components. In the numerator, our imaginary components will not disappear since we're not multiplying by the conjugate of the numerator, but that's okay. It's okay to have imaginary numbers in your numerator. We just don't want them in the denominator, just like irrational numbers. Just a rule someone came up with. So when simplifying this one, we end up with -20 plus 7 and 28I plus 5I. You can break this down into the real component and the imaginary component, or you could leave your answer like this. Either one would be correct. On the last one, you can multiply the numerator and the denominator by the conjugate if you want, -3I. But a shorter way of doing this one is just simply multiplying the numerator and the denominator by I, because then the denominator will say 3I squared, and I squared is just -1. And so we just have -3 in the denominator. And then in our numerator, when we distribute the I, we have -2I minus 5I squared, which turns into +5 minus 2I. So why do we need to do this at all? We've been solving quadratic equations, and so far all of our solutions have been real, which means our solutions have been x-intercepts on our graph. But we know that not every parabola crosses the x-axis. And so if a parabola does not cross the x-axis, it does not have real solutions. It has imaginary solutions. So this first example, x squared plus 4, if you were to graph that, that would be a parabola that does not cross the x-axis. And so if I solve it, I get x squared equals -4. Take the square root of both sides. When we take the square root of any number, when we're solving, we need to include the plus or minus sign, and the square root of -4 is 2i. So because this graph, this parabola would not cross the x-axis, it has two imaginary solutions at 2i and -2i. So similar thing with example 2. We're going to solve using square roots since we can isolate the x pretty easily. So when I try to isolate the x, I'm just getting rid of one thing at a time to get x by itself. Now I need to take the square root of both sides. The square root of -18 is not a perfect square, so we need to simplify it. And it's imaginary because we're taking the square root of a negative. So if you simplify the square root of 18, you get 3 root 2. So this is 3i root 2 since it's imaginary. And then we can never forget the plus or minus sign. Imaginary solutions always come in pairs. On our last example, we can do this one by solving by square roots also because we can isolate this x pretty easily. The first thing we need to do to isolate the x, though, is to divide both sides by -5. Then we need to take the square root of both sides. Right now that -2 is trapped in the parentheses, so we cannot add 2 to both sides. We need to go ahead and stop and take the square root of both sides. So the square and the square root cancel each other out. When I take the square root of -6, it's going to be imaginary. Square root of 6 does not simplify. And so we'd have plus or minus I, because it's imaginary, root 6, because the square root of 6 can't be simplified. And then we still have one more step in this case. We need to add this 2 over to isolate the x. And we always write the real component in part, so 2 plus or in front, sorry. So 2 plus or minus I root 6. Another thing I want to point out is that if it says we're finding the zeros of a quadratic function, that's the same thing as finding the x-intercepts or finding the solutions. It just means we're going to be plugging in a 0 for the y, and then we're going to solve just like we've been doing. So we substituted a 0 there so that we're finding the x-intercepts. If I'm going to solve to get x by itself, I'm going to subtract 1 first. Then I'm going to divide both sides by 9, so that x squared equals -1/9. And then to get rid of the squared, we're going to take the square root of both sides. This is imaginary because we're taking the square root of a negative. Don't forget your plus or minus, and the square root of 1/9 is 1/3. Because the square root of 1 is 1 and the square root of 9 is 3. And let me write that better. I'm going to write it as plus or minus 1/3 I. This I do not find nearly as important, but you can plot complex numbers if you make the y-axis your imaginary axis and the x-axis your real axis. So if I'm plotting the number 3 minus 2i, that means 3 is my real number and -2i is my imaginary number. So I'm going to go 3 over on my real axis, 1, 2, 3, and then down 2 on my imaginary. So there is the real component of 3, the imaginary component of -2. So next one, -2 plus 4i. Real is -2, that's my x. Imaginary is 4. So that would go there. If I only have an imaginary component, then my real is 0, and I'm just going up to 3 on my imaginary axis. I'm going to skip down to e. If I only have a real component, then I'm going over to -1 on my real axis, and then I'm not going up or down at all because I have no imaginary component. So if we were going to write the coordinates for z, this point right down here, the real component would be 5, because we went right 5, and we went down 5. So my imaginary component would be negative 5i.